Hello and welcome to episode 1 in this series about Coxeter groups. In this video we're going to examine what a Coxeter group is, some interesting properties, and then also go through some examples. We do assume a graduate level understanding of group theory and reflection groups. If you're unfamiliar with those or would just like a refresher, then I recommend you watch the episode 0 in this series, which can be found in the description below. Right, well, let's get started. To understand Coxeter groups, we must first sort of ask ourselves, what is the point? Okay, so Coxeter groups seek to abstractize reflection groups, and yes, that is a word. So where a reflection group, which we discussed in the last video, are generated by reflections, okay, a Coxeter group in a more abstract sense is generated by elements of order 2. So if we have a group W, okay, and generating set S, so that is equal to W, okay, then to make it for this to be a Coxeter group, we must first define a function m, which goes from s and s to n, okay, and it is governed by the following relations. So first of all, we have for all s1 and s2 in S, okay, S1, S2, all to the power of m of S1, S2 is equal to 1, okay. Second rule, m of S1 and S2 equals 1 if and only if S1 equals S2, and then finally m of S1, S2 equals m of S2, S1, and this is always greater than or equal to 2, as long as S1 is not equal to S2. Okay, so what is this function, right? Well, it's basically a function of to find the order of your elements, of your generators, I mean. Okay, and their product, and their pairwise products, that is. Okay, and if all of these are satisfied, okay, if all of these are satisfied, then W is a Coxeter group, and the two of these together in this form a Coxeter system. Okay, now I'd like to now define a length function on a Coxeter group, okay, because that way we'll be able to compare different elements in W, okay, and I would say that the most natural way to define the length of an element is through its minimal decomposition, okay, which I believe we did discuss in episode 0. Okay, so let's go ahead and define that. So we say that L takes an element from W, okay, to the natural numbers, okay, and L of W is the fewest, yeah, that spells fewest, the fewest generators required to write W, which is in W. Okay, that is the length. Okay, and by default we say that the identity element has length 0. Okay, some interesting properties about the length function include the length of W is equal to the length of W inverse. The length of W is 1 if and only if W is in S. So basically W is a generator. Okay. 3, the modulus of the lengths of W1 subtract W2, okay, is less than or equal to the length of W1 times W2, and that is less than or equal to the length of W1 plus length W2. So W1 and 2 are these elements in our Coxeter group, okay, and this thing is true. It looks a bit confusing, but it's a thing. Don't worry about it too much. Okay, it's a nice property, and if you want to see a proof of it, then check out my project, which I've linked in the description below. Okay, and then finally, property number 4, the modulus of the length of W minus 1 is less than or equal to the length of WS, and that is less than or equal to the length of W plus 1. Okay, and number 4 is actually just a special case of number 3. Okay, where we changed W2 to be a generator. Okay, because we know generators have length 1, and so yeah, you just change things around basically. Okay, these are nice. These are sort of nice properties about the length function that become useful later on when we do calculations and things with the length function. Okay, before we move on, okay, I would like to define something called parabolic subgroups. Okay, so let's write that out. So parabolic subgroups. Okay, and these are subgroups generated by I, which is contained in S. But so it's basically, so if you've got a Coxeter system, WS, where S is the generating set, then the group, generated by I, okay, and we write it like this, okay, so this is a parabolic subgroup, okay, and then we also say that a Coxeter group is irreducible if all the parabolic subgroups that are generated by a singular generator, okay, if these are all basically the same, Sj, okay, if these are all the same, and that is in this, okay, then we say that the Coxeter group W is irreducible. Okay. Now I've said the same, but that's the isomorphic symbol, you know, as we discussed before. Not the same, but the same structure. Okay, that's all it is. All right, now that we've gone through those definitions, okay, I want to mention a nice corollary regarding reflections in Coxeter groups. Okay, and so it turns out that all reflections in W have the form WS W inverse. Okay, so if you want a reflection, if you take any reflection, okay, so an element of order 2, okay, you can write it in this form. This may not be its minimal form, okay, but that is definitely its form. It can be written in this way. And if you would like to see a proof of this, then you can check out the project, which is in the description. I believe this is corollary 2.1.1. It's corollary of a proposition. Okay, so you might want to have a read of that before you look at the proof for this. Okay, but yeah, you can look at that if you like. Okay, a couple more quick things about Coxeter groups. T L of W. Okay, so this is little w. This refers to the left associated reflections. Okay, and so this is all the reflections T. Okay, if T is the reflection set, so this is, you know, all possible reflections, okay, then such that the length of TW is smaller than the length of W. Basically, it's all, TL of W is all the reflections, little t, such that you multiply by W by T on the left, you get a length, a new element that has a shorter length than W. Okay, and we also have DL of W. Okay, and this is defined as the left descent set. Okay, and this is TL of W intersected with the generating set. So basically all the generators that shorten W. Okay, that's all nice. That's great. Okay, we've gone through some abstract things. Let's have a look at an example. And the example we're going to go through is the dihedral group D6. Okay. Now the traditional so D6 should clarify, this is the group of symmetries on a hexagon, and the traditional presentation and generating set. Okay, if we have the generating set S, the traditional one is to use R and S, so rotation of 60 degrees and a reflection could be in any axis. We'll stick to vertical because that's what we used last time. Okay, and the rules are that R to the 6 equals 1, S squared equals 1, and SRS equals R to the 5. Oh, there. Okay, so those are the rules. Okay, and you know, you can see very quickly this is not a Coxeter group. Okay, because R to the 6, you know, R is a generator, but it does not have order 2. So, thing is, what we can do here is we can make it a Coxeter group. Okay, so let's change. So we'd say little s, and we're going to call that little s1. Okay, and we're going to say that little s2 is the reflection RS. Okay, now we can, now this implies, okay, that S2 times S1 equals RS times S, which is R. Okay, so S1 and S2 do indeed generate D6, okay, because you can form R, and so we've got S and R, and so, you know, so you go through the motions and you can indeed get the whole of D6. So that's good, okay? Okay, so this is, so now let's rename the set S1 and S2. Okay, we've got a new generating set, and we'll call that S bar. Okay, so D6 with S bar is indeed a Coxeter system. Okay, it's got rank 2. So the rank just refers to how many generators make up the generating set. Okay, and let's have a look at the length function in action. So if we have length of, so let's say W equals S1, then length of W equals length of S1, which is 1, easy enough. And if W equals S2, S1, S2, S1, okay, then length W, I'm not going to write that all out again, but that's 4, okay? We can observe then that okay, we also have these things called subwords in Coxeter groups, and actually this sort of replies to all sets where you've written things out in this way. And a subword, so W written in this way is a word, okay, or the word word refers to writing something written like this, and a subword is just, you know, if you chop off at some point, you know, what you get. So S2, S1, S2 is a subword, S1, S2 is, and so on. You could go through and work out, you know, all of them if you like. But, you know, that's effort. Okay. And that's the end of that example. Okay. And yeah, we will come back to D6 at some point. Okay. And if we do, we'll be using the generating set S bar. Okay, because, you know, that's the Coxeter group. That's how to make it a Coxeter group. Okay, what can we do with this though? Well, first of all, we can actually draw a Cayley graph for both presentations. Okay, and I've drawn those over there. Okay. And, you know, you can see very quickly what, you know, a lot of differences between them. So, for example, the Cayley graph of the standard presentation, all of the nodes in that have degree 3, whereas that of the Coxeter presentation, you know, the nodes can either be 2, 3, or 4. Okay, and its structure is very different. Okay, you know, it's a bit, so it's not like, you know, you're just writing things differently and you don't really end up with anything different. You actually do end up with a really totally different structure, which I think, you know, I think it's really cool. I would like to look at the strong exchange condition and the deletion condition. Okay, and they say, okay, that if so, let W equal S1 up to SR, okay. So you know, let W be some element basically. Okay, and this is in a Coxeter group W. Okay, and this is not necessarily reduced. Okay, so it might not be in its minimal form. Okay, but the strong exchange condition says that if you have a reflection T, which is in the right not descent, just the right reflection group, okay, then there is an index I such that WT equals S1 SI hat and then SR, where this hat here means emission. So basically, okay, what the strong exchange condition says, Okay, what this says is that if you multiply by a reflection that you know shortens the element W, then it shortens it by 1, and you can find it shortens it by precisely 1. Okay, well, not necessarily, because it might not be in a reduced form, and what might happen is you might end up with SJ and SJ on both sides, so they would cancel. But the point is that you can omit a single element from its from its decomposition, okay, and get the element WT, okay, and that's really cool. The interesting thing with this is that if S1 SR is reduced, okay, so this is the minimal decomposition, then I is unique. So that element that we omit is unique, okay? And the deletion condition, so that was the strong exchange condition. The deletion condition says that so if W equals S1 up to SR, okay, and the length of W is less than R, okay, so this is not in its minimal form, okay, then there exist indices I and J, okay, with I less than J, for which W equals S1 SI omitted, SJ omitted, and then SR. So what the deletion condition says is that you can, if you've got W, okay, and it's not in a reduced form, okay, then there are two elements in its decomposition, okay, that you can delete, and then get a reduced form. And what you can actually do is you can repeat this over and over again, okay, and you would eventually find a reduced form for W. Which, I mean, this is pretty interesting stuff, right? This is pretty cool stuff. Okay. I'm not going to prove these here because they're quite long proofs and it's a bit beyond the scope of this series. But if you're interested and want to see the proofs, then I recommend you read the project that I wrote. Again, link in the description. Right. Okay. Nice. That's nice. Oh my gosh, my nose is so itchy. Yes, I'm going to have to. Okay. All right. Let's talk about permutation groups now. Okay. And so this is the group of permutations on n elements. So Sn is what we're looking at. Okay, and Sn is indeed a permutation. It's a permutation group, but it's also a Coxeter group. Okay, with adjacent transpositions forming the generating set. So, oh no, we don't want curly brackets. We want normal brackets. So S is adjacent transpositions. Okay, so what are adjacent transpositions? Well, they are just elements of the form k plus 1. Okay, so it could be something like 1, 2, or 23, 24. Okay, those are adjacent transpositions. Okay, and again, I proved this in the project. Okay, I'm not going to do that here. You can just take my word for it. Okay, but now what we want to do is I want to define something called the inversion number. Okay, so inversion number. Okay, so let x be in Sn. Okay, then the inversion number, so inv of x, okay, is the number of pairs I, j, okay, with I less than j that x inverts. Inverts. Yeah. Okay, so what does that mean? So just x of I is greater than x of j. All right. So basically, you know, you've got I less than j here. You send it through x, through this permutation, and you end up with x of I being bigger than x of j. So you swap them over, basically. Okay, or not necessarily swap them over, but you end up with something where the sizes are swapped. Okay. If you want to write this in sort of set notation, then you can write inv of x is equal to the size of the set ij such that such that I is less than j and x of I is greater than x of j. Now, maybe covering both of those is a bit overkill, but you know, if you don't get it this way, you can at least get it this way, or hopefully you do. Okay. Okay, and it can actually be shown that the length of a permutation under the Coxeter presentation is equal to the element inversion number. And again, I won't prove that here, but you know, check the project in the description below. But that's all rather abstract. How does this work as in an example, you know, in real permutation groups? So let's have a look at the permutation group S5. Okay, so this is the group of permutations on 5 elements. Yeah. Okay, 5. So its generating set S is equal to 1, 2, 2, 3, 3, 4, and 4, 5. Okay, it's got 4 of those, and yeah. And what we're going to do here is we're going to write 1, 2, 3, and 4 in blue to refer to these, just because I don't want to have to keep writing out the whole lot, okay, with all the brackets and stuff. That's effort. Okay, that's effort that I don't want to put in. Okay, so let's work out the inversion number of a random element. Let's take green. Okay, and let's take the element W equals 2, 4, 3, 5, 1. Okay, so we want to calculate the number of pairs ij with I less than j, which when acted upon by W, we have W of I is greater than W of j. So let's work out the appropriate pairs and work out what they get sent to. So we have 1, 2, and I'll speed this bit up, I think. Okay. Okay, so that's all the ordered pairs such that the first one is smaller than the second. Okay, so the elements under W for 1, 2 get sent to, so 1 gets sent to 2 and 2 gets sent to 4. Okay, 1 again sent to 2, 3 is sent to 5. Okay, so what have we ended up with? Well, if we go through and count these, okay, then what have we got? We've got 1, 2, 3, 4, 5, 6. Okay, so the inversion number of W equals 6. All right, so that should be the length, right? Let's work it out. Okay, let's work out the length of W, you know, in sort of an abstract way. Yeah. Okay. So we have W equals 2, 4, 3, 5, 1. Okay. If we split this up, then we get that we get 2, 4, 3, 4, 3, 5, and 4, 5. Okay. Then changing these as appropriate into generators, we get 2, 3, 2, 3, 3, 4, 3, 1, 2, 3, 4, 3, 2, 1. And if you go through all the stuff about you know, reordering elements in permutation groups and with generators and stuff, and what you get from what things and all that stuff. Okay, it takes a bit of time, and you know, if you want to do it, I'll leave it as an exercise to you. Okay, but what you should get is that W equals 3, 1, 2, 3, 4, 3. Okay, that is its minimal decomposition, and it does indeed have 6 elements. Okay, so you know, I would say that's a win. That's a win for Coxeter groups, right? Okay, because the thing is, this method of calculating the length is insane. Okay, it takes ages, whereas this method just quickly calculate the inversion number. You know, this is a lot quicker. Okay, this would be a lot quicker. So yeah, you know, it's a nice property that they have. And that's the end. That's the end of this video. I hope you enjoyed it. If you did, you know, hit like, hit subscribe, do all the things. Okay, I've put a link, as I kept saying before, to my master's project. That's in the description below. So if you'd like to read it about all the stuff we've done today, and also stuff I didn't cover and stuff that I will cover in future videos, then, you know, by all means, go ahead and do that. Otherwise, keep an eye out for more videos in this series, and I'll catch you in the next one.